Sorry. All right. So now we're recording. Hello, everybody. This is the CS 365 midterm review session. Got my two friends here. Yeah. So Adam, you were saying you wanted to go over. You were making a thing, like for the review session.
Like I was I was thinking of making like a condensed cheat sheet just with the stuff that's very formulaic for reference, like the logical precedents, maybe list in brief all the types of all the methods we've learned so far for proving direct proof by cases, things like that. Just to have it all in one spot.
Yeah.
And then there's also I transcribed the slides that he went over at the end of the last class, all the practice problems. I put all those in a single document that's in the resource channel on the 365 Discord as well. So you can practice that and then look up the answers in the video.
I saw that. That was really cool. You've been posting the homework templates too. That's super cool, you man. Thank you for all that.
Yeah, I feel bad because a lot of them have been pretty riddled with typos that I don't always catch because I just copy and paste it from the PDF. And then sometimes it's into Word, which I know I probably shouldn't be using as much, but I figure a lot of people have it. Sometimes it recognizes a symbol and sometimes it doesn't, and it'll substitute it with something else. And I don't always catch that. But oh well.
Gotcha. It's still a thought that counts. That's pretty cool. Yeah.
I do it anyway for myself, so I thought it takes 3 seconds to throw it in there as well. So what was the plan for today? I'm sorry, I'm looking over my stuff. Are we gonna go over, I don't know, old quizzes, old homework? Are we gonna go over the review thing, or are we just gonna pick topics out of a hat?
Well, I was thinking
start with the review thing.
Yeah, I was thinking the review thing since
since we just have it right here.
Yeah, and I deliberately tuned out while he was going over it, so I don't remember any of the.
Nice.
Okay, yeah. So number one, write the contrapositive, converse, and inverse of the following statement. If you try hard, then you will win.
All right. Could you, if it's possible, could you share your screen? Like, I'm assuming you just have the
question. Sure, yeah. That's why I'm looking this way. I have it on my other screen.
I need to get like a USB splitter or something, because in order to use my webcam, I have to sacrifice my mouse or my keyboard. So
yeah, I want to get one for my I'm in embedded systems right now. I want to get one because I have like the Arduino and and like the little oscilloscope thing as well.
Yeah, I just didn't even turn in my lab for that. I was too stressed. But
I feel like I know this is a tangent, but I did that, and then based on what everyone else is saying, I realized I have serious reading comprehension issues with that lab and did about half of it completely wrong because I misinterpreted what these instructions were saying. But I took screenshots, I uploaded code, so hopefully it still gives me something because I thought I was doing the right thing, but
yeah. By the way, is there a way to allow us to annotate on the screen?
I don't know.
It's a little tricky. So it's at the top, and then it's like 3 little dots. You got to click on like more.
Enable annotation for others.
Yeah.
Okay.
Yes, there it is.
Want to try it?
Wonderful. Yes.
Yeah.
It is there.
And then so far I was thinking like we could say if you try hard as P, and then you will win as Q, and then the contrapositive would just be delta Q implies delta P. So then you could say like if you don't win, then you didn't try hard. Does that sound good for contrapositive?
Yeah, but I mean,
if you don't win, you didn't try hard, you said?
Yeah. It sounds a little funky, but that would be delta Q implies delta P.
So the regular statement right now is a simple.
I'm kind of iffy on your negation of the Q. Because
Gotcha.
don't isn't exactly the negation of will. I would say will not.
Gotcha.
So the basic, if we take P to be you try hard and Q to be you will win, the basic statement as it stands is just a simple implication. If P, then Q.
Yeah.
So then the converse is, let me see if I haven't looked this up, so let me see if I can remember this. Converse is, I know, well, let me do contrapositive. I remember that one.
Yeah, contrapositive is, that's the easiest one for me.
It's like not Q implies not P, right?
Yeah.
Yeah. Also remember that the inverse of the converse is the contrapositive.
Yeah, there's a symmetry.
And vice versa. Like if you take the converse of the inverse, it's also the contrapositive. So.
That's weird. Inverse is inverse of what?
That's where you flip them, so that would be Q implies P.
That's
for
the inverse.
Okay.
Yeah.
No, that's converse.
Oh,
Converse,
is it?
Q implies.
Yeah.
My bad. My B. Gotcha. Sorry about that, Adam.
So then inverse is not Q implies P?
Yeah.
Close, but no.
It would be not P implies not Q.
Yeah.
Oh,
You're just putting a negation in front of each one.
You just negate the regular statement.
Yeah.
Yeah.
And converse is flipped, which I'm glad I
keep messing this up.
Forgot about that.
Why does it keep changing the font on this?
You're not allowed to have one font.
I know. I'm sure someone out there is screaming that I'm doing this in Word with the symbols and stuff, but oh well. So then to translate this in English, is he? Because if it says, I mean, I assume they want to translate it in English. So then, if you is you will win. You will win if you try hard.
Careful. That statement is the exact same statement that it gave us.
Yeah, I would say
the if needs to go at the beginning.
You're right. You're right. Yeah.
Yeah. Follow the format if, comma, then.
Yeah. Good call.
Yeah. Because trust me, I've done that so many times, and fuck, it never feels good.
That's not really telling us anything. So
yeah.
So then, if you don't, oh wait, you were just talking to Gabriel about this.
Yeah.
You say say don't here.
If you will not, or if you won't, either will work. But yeah.
Yeah.
Just because I think it's safer to keep it in the same time tense. You know?
Yeah. I would say didn't try here. Did not try, because you don't say try not.
I would say the same thing, but I'm not sure.
I'd say didn't try hard.
Cool. Did not works too, right?
Yeah, I mean, contractions.
Same thing.
Yeah. So
I don't think he's gonna pull a English teacher hissy fit. So.
Hope not.
So then, if we wrote our contrapositive properly, why am I doing that? Then we can just do some of this action, because I hate typing any more than I have to.
Yeah. That looks good to me. I mean, as long as those make grammatical sense.
If you did not try hard, then you will not win. Yeah.
Yeah, that one sounds
right.
Okay.
Cool.
And if you want to double check me that I'm right on the definitions of converse and inverse.
Yeah, let me pull up
I think I am, but it's better to be safe and not learn false things.
That's
definitely.
I'll flip to the book.
That's
chapter 1, right?
Propositional logic, right?
Yeah, it's page 9.
Page 9.
Then it's like right below example 11. Yeah.
Contrapart. Yep. Symbolically, that's correct. So cool.
All right.
Now, the tautology is we have to prove that it's true always or either way.
Always.
Tautology is basically just saying it's a trivial statement because it's always true.
The opposite of a tautology is a vacuous.
I don't remember the word.
I'll look for it.
We never use
Like
it.
it's always false.
I know that the notation for it was an I think. A capital I.
Like imaginary. Oh.
I think I remember that, but
applications of propositional logic. Let's see. I'm just scanning the textbook here. Consistent.
I know there's a specific word for it, but
yeah, logic circuits. Oh, we skipped this part.
Yeah, we did skip logic circuits.
Honestly, if the term shows up, I'm sure we'd recognize
contradiction. Duh. That's if it's always false.
Okay.
I don't think that's the right word.
Yeah, it says page 26, 1.3, a compound proposition that is always true no matter what the truth values for the propositional variables that occur in it is a tautology. If it is always false, then it's a contradiction. If it's neither a tautology nor a contradiction, then it's a contingency. This is for a compound proposition.
Gotcha. And that was page 26.
Yeah.
Gotcha.
Start of 1.3.
Tautology is presumably a contingent statement. Okay.
All right. So I really like these ones because it reminds me of Boolean, just stuff like that with the Morgans and all that kind of stuff. So usually I like to start like breaking up the whole thing from like inside out, you know? So like the first thing that I think we could break up
this nested P equals Q naught. So we break down the implication. It's an implication is the same as and not on whatever the predicate is, right? Or the second statement.
No.
I think it's the other way around.
So you're thinking of the negation of a thing. The simplification is not P or Q here.
Yeah.
It would normally be not P. Or I mean, it's
yeah, not P or Q.
It's not P or not Q here because we have not Q as
the not Q
the conclusion.
I didn't even see that.
Because when it's P implies Q, it's not P or Q.
Space out a little bit.
Can you zoom in a little bit, Adam? Because I didn't even see that not Q thing.
Zoom in?
Yeah, if possible.
Oh, yeah.
Yay. All right. That's way better. Thank you.
There we go.
Cool. My eyes. Perfect.
And so there we could actually just distribute
this Q into it.
Yeah.
Yeah, so then this becomes that, but then, oh yeah, and then this just, how does distribution work? So it's like that.
Yeah.
Yeah, that's what I got too. I always think of it like foil in a way. So like I know that
it's exactly what it is.
Yeah,
I just
think of it as foil.
I never remember foil. It's just how it is. Okay, now this though, if it's true and false, that's always false. So this whole thing goes to 0, right?
Mm-hmm.
Yep.
Doing a fancy little strike through. So actually, I don't know if he wants us to do 0.
Is there a law we have to specify to knock that out, or could we just say
to do the distribute thing?
Well, no, just like when we say it's false, like we could just like get rid of it. Is that like a law? Or could we just say?
If you just notate it like Adam did there, that you should be fine.
Gotcha.
So
I'm trying to find the specific.
Oh, it's also an identity law. I just flipped to it on accident.
Okay, yeah.
Yeah. Okay, cool.
Yeah, I should actually. Okay, yeah, an identity law. So anything ORed with false is equivalent to that original statement itself. So that false
completely
just drops out.
Yeah. Cool. And then we could do that thing again.
Yeah. So then to break this up again, so then this is replaced with an or. Definitely gonna have, and then this is not.
Yep.
Okay. Then we can distribute that negation in. And that will invert this sign. So and then this becomes
as normal
regular P.
Yeah. And then
Now
associativity.
We can do some associativity stuff with that. And just like with, or no, this is
that's a tautology right there.
Yeah.
And
This
so
is
that's
always true by the negation law. So
so then domination law.
Yeah, so then this is always true. Exactly, and anything ORed with true is just true. Ta-da!
Yay!
Fancy.
All right. Cool.
Clear up some of this white space. Okay.
Should we list the laws next to it, in the actual exam? Do you think?
I don't know. That's kind of tedious. I imagine. I would hope that that's not really required. Something like this is probably going to be multiple choice anyway. Maybe I have to pull back the quizzes and see what kind of questions we have for this stuff.
Well, that was question 2, I think, or quiz 2, I believe.
Let me pull that up really quick.
Yeah, it was quiz 2, question 1 had stuff like that. It would just say,
so it's just, is
it
exactly, is this a tautology or not? Yeah. So I think as long as you know how to do these operations to get to this answer, it should be fine.
Gotcha. Cool.
Okay. Suppose the variable x, I didn't really do any of the italics with this stuff, that's kind of tedious, but suppose the variable x represents students, y represents courses, and a bunch of functions follow here, or not functions, predicate statements, I guess. Write this statement using these predicates and any needed quantifiers. So this is we had a homework that was all this stuff. This is also in quiz 2, actually. Question number 3
and 4.
Yeah,
but mostly 3 to convert it. Yeah.
I mean 5 because 4 is just universal qualifiers and existential.
Oh yeah, 5. Oops. All right. Okay. Well, for this one, you would just say so students is a keyword for sure. So we're just using X, and then we're saying all of X, and that's another keyword. So that just kind of tells us
I have that in my. So all students is just that. If X is a student, and then if they are a freshman, it's just F of X, because it doesn't specify whether or not they're full time or anything. It just says they're freshmen. So isn't that enough right there?
Yeah, I think that's good. Because just saying every student's a freshman. Yeah,
exactly.
Easy peasy. Cool.
There. Okay. Every freshman. So now this is actually, if they're a freshman, then they is a full-time student. So this is actually taking what we have here, right, and adding an extra condition to it.
Yep.
So they are freshmen. Now, I always get this mixed up because one of them, either the universal or the existential, it feels like it's almost always the implication. And the other one isn't. Is this just and? They are a freshman and they are a full-time student?
No, it's a conditional. Because you said if they're a freshman, then they're a full-time student.
Because otherwise you'd be saying every student is both a freshman and a full-time student.
Yeah.
You're right, yeah. So it's just.
And then you got to put parentheses around that whole thing.
Okay, yeah, that makes more sense.
And so then whenever you do conditions with these, it's good to check yourself by using the contrapositive. So
Okay.
to see if it still makes sense. So does it still make sense to say for every student, if they are not a full-time student, they are not a freshman?
Yeah.
I'd say so.
Yeah, I'd say so too.
Oh, yeah. If they're not a full-time student, it rules out them being a freshman. They could be something else, but they can't be a freshman. Yeah. Okay. No math courses upper level. That's a lie.
So that's still the universal, I think. It says like no math course, like in all the courses.
It's making a sweeping statement here. So that's still now course though. That's going to be Y.
Yeah.
So all Y's, all courses, such that where's math? Here it is.
Yeah.
So all courses that are math courses, upper level is. So this is actually okay. So this is interesting. If it's saying no math course is doing this, then I apply the negation in front of this whole thing, right?
No, I think you would apply it after, because then it would say.
This says this says a math course is upper level, and then this says that applies for all. Like if a course is a math course, then it is also upper level. This is saying not that, right? Well, no, if we distributed this in though, it would say if it's not a math course and it is not upper level.
I would just put it in front of the U, like, and see if that makes more sense. Because I just feel like that would be less, like if it's a math course, then it's not upper level.
Yeah.
I don't know if the other way works too, though. Like I'm trying to think of if that would work the other way now.
We could probably do a truth table and.
Yeah, that sounds good. We could do that real quick.
It wouldn't be quick, but we can do it. All right.
I think that works.
So I guess I probably don't need this many columns, but we're already here, so whatever. So we'll just do.
No,
it kind of doesn't work already. Whatever.
I lied.
Not this. And then what was the alternative statement we were going to do? We were going to do this, but with a negation in front.
And the whole thing, yeah. I didn't even know you could make tables in Word.
No.
No, I always just handwrite all my stuff.
My handwriting is atrocious. I wouldn't inflict that on anybody, so I type all this. That should be enough, right? It should be enough,
that's more than enough. Yeah.
Center all this. Okay. So I kind of hate how everything starts true, because I'm used to starting with everything false, but they just do it their way. Okay. And then this is just inverted.
Yeah.
So if this is true and that's true, oh no, it's not.
Right, so that would be false.
And this is false. Yeah, that's the one time it's false. Every other time it should be true. All right, let's double check this. So if this is false, and that still be true. Yes, this is false. That would be false. That's true. And if this is true, that would be true. Yep. Okay, good. So now I think I'll just do the original one in the parentheses, and then I'll just nod it. It's probably easier than trying to do it mentally.
Okay. And that one's true and nodded.
Yeah, so this is true, not, it's actually false.
And that one's false and knotted.
This would be false, so that's knotted to true.
Right, and then that one.
And then the other ones have to be,
which is false.
Oh yeah, you're right.
The third one. Yeah, that'd be false.
So these are not equivalent statements at all.
No.
Yep. Okay, so which one is correct then?
So the one that you have written, try to put that into words.
Which one? Oh, this one up here?
Yeah.
Yeah.
This one here. So
this is saying all courses, if it's a math course, it is, or then it is not high level, upper level. My goodness.
does that work?
I think it does.
Yeah, that sounds good. How would the other one go in words?
This other one would be
still all courses.
I'm going to type it out normally, then just apply not. So this would be is a course, then it is upper level, and then whatever. This is not implication, this is like translation.
So if it is not a math course.
Yeah, then if it is not a math course, and then this becomes or. It's or.
Or.
Yeah.
Or it is if it is not. Yeah, I don't think that one would work. I don't think so.
Which we showed with the truth table. These are not equivalent statements. So
yeah, I'm glad we thought about it though. I'm glad that we broke it up. And, you know.
So now with the first one, to make sure we try the contrapositive.
So
for every course, if it is upper level, then it is not a math course. Seems to work.
Yeah.
Yeah. Cool.
If it is yeah. All right. Fancy.
Very fancy.
Okay.
All right. Scary proof time.
Yeah. Now we're out of the
the comfort zone.
Yeah. Now it's time for the boss fight. So, so the following theorem of x and y are odd integers, then x plus y is even. Give a proof by contradiction. So proof by contradiction means show that, I'm just doing this from memory, show that it is false unless it's true. No, show
that what is false.
Isn't it the end?
Right.
I thought it was like you take the end one and you say, hey, that's odd. So for example, x plus y is odd. And then you try to prove that. And if it contradicts x and y, so like if you say x plus y is odd, and then you try to kind of go backwards and just be like x is and y is, and then if x is still odd and y is odd, then it contradicts that statement. Is that right? That sounds wrong.
So would this be even integers or is this still odd?
Well, you would assume that they're odd, and then if it's even, in the case where x plus y is odd, then you contradicted yourself because the statement is given that x and y are odd. So maybe
I think you're making it a little bit harder on yourself than you need it to be.
Okay, let's make it easier. What do we do?
So you had it right at first, actually.
Okay.
Proof by contradiction is you assume that the statement is false. When is an implication false? An implication is false when P is true and Q is false. So we make Q negated. So if we negate Q, so we say if x and y are odd integers, then x plus y is odd. Then we're setting up a proof by contradiction.
So this?
Yeah, in this particular case, that would work. Yeah.
Okay.
Gotcha.
Kind of.
Oh,
more
no, let me know. I don't want to be
Okay.
leading myself or others astray.
Okay.
So please let
So-
me know if this is not correct.
So you know the truth table of an implication? How it's
Yeah,
true,
it's
false, true,
always
true.
true unless P is true and Q is false. That's the only time
Yeah.
it's false.
So the exact thing that we're assuming here is we're assuming P and not Q. We're not assuming P implies not Q.
Oh,
P
okay.
and not Q, because that is our specific case in which the statement is false. So now we're looking for a contradiction of that, and that contradiction tells us that our original assumption of the statement being false was wrong, and thus the original prompt is true. That's what we're doing with proof by contradiction. I think it's a really messy way of proving things, but it's way too useful to not use. So I like to default to contraposition just because contraposition is nice. Yeah. And so obviously you can say not even is odd, but
yeah, I guess.
And so then now that you have this format, you can now assess, okay, what's going to be the most useful. Because with proof by contradiction, you actually haven't set up the way you're proving yet, because you still need to decide whether you're proving directly or indirectly. So do you want to use direct proof or contraposition? Basically, which do you think will be easier?
Contraposition.
I usually start with a direct proof and I only go to something else that doesn't work. That's probably not very efficient.
Direct proof is actually easier here.
Direct proof
then. Because it tells us to assume that x and y are odd and then show that x plus y is odd now. So if we're doing that, we can say, okay, x equals this definition of an odd integer, and y equals this same definition, but we're going to use a different variable. We'll call it like k and k prime or something. And then we'll show that when we add them together, we get 2k plus 2k prime plus 1, which of course is divisible by 2. So then it's even, so we get a contradiction.
Let me write out the definitions.
Yeah.
So this is 2n if it's even and if it's odd. Right? That's the definition of even odd? Okay. Mm-hmm. So we're looking for these forms. So if we're saying if they're odd integers, then if they are odd, then their sum will be odd. We want to show that that is false, that two odd integers added together actually become even. So it'll look like 2n at the end. That's how we know that we have a contradiction and thus the original statement is true.
Yeah, so we're just adding two odd integers together, and so like don't overthink it.
I'm not. I'm just trying to be very careful and methodical.
So how about you proceed, and I'll just be here. I'll be a guiding hand.
So I think,
did we do any divides by proofs in this?
Divide by?
Yeah, divides by. So like proving that like 2 divides 4, for example. I don't remember if we did that at all.
I don't think so.
Not sure.
Okay, well, if you guys don't remember it, he probably didn't go over it at all. So unless he decides to throw a major curveball, we probably don't need to go over it.
It doesn't seem like it. There haven't really been a lot of trick questions on the quizzes or anything like that.
No, he's pretty generous.
Yeah. All things considered. So
you guys should be familiar with how to prove rationality, though. That's going to be one that's probably going to be on the test.
Yeah, when you have to show that they're a ratio of real numbers such that the denominator is not 0.
Yeah. Or for example, he might ask a question like, oh yeah, prove that radical 2 is irrational.
Yeah.
Or prove that the product of 2 irrational numbers is also irrational.
We should go over those ones after.
It was like a homework question, I think.
Yeah.
Sounds
Yeah, I
familiar.
think both of those were homework questions, or at least reviewed in class.
Mhm. Okay, gotta focus here. So what are we doing? Okay, so let them be odd integers. We'll just, and then,
Therefore, define them.
yeah.
So x equals 2n plus 1. Yeah. And same with y.
Well, I mean, could it though? Because they're not necessarily both based on n. This implies it's the same n for each. So I'll say it's
You can use a different variable, yeah.
2n.
And then generally, at this level of proofwriting, you would say for n comma m are elements of the real integers. What the hell was that?
Whoa.
Excuse me?
flexing a little bit
Okay, magic.
like that, right? All right, it's actually backwards, isn't it?
So we don't want to build a set here.
Okay, I'm getting ahead of myself.
Because they're not elements of the set. We're probably going to be doing that in the second half of the semester, stuff like that.
Yeah, that thing I did, by the way, that's I looked up a bunch of these codes. I have like a whole picture of all these different mathematical symbols. There's a bunch of number codes that all start with 22 and then some other digits. If you select that and then you do Alt and X, yeah, it has to be the number exactly. You can't have any spaces in there or it won't figure it out.
Dang, dude.
That's the code for element of. You can do the same thing with syllogisms, subsets, all kinds of things.
I love that. All right.
Yeah.
And I have to look into that later.
I still use this symbol thing up here because it's easier than I only have some of them memorized, but you know.
Yeah. But yeah, so and now you just add them.
Yeah. I use semicolons a lot. I know it's probably not very rigorous, but whatever.
It doesn't matter.
Yeah, it's all good.
As long as you're clearly like delineating statements, that's fine. So it does actually work perfectly well. I know some professors get super pissy if you don't have your proof in like a normal block. Like if you have everything super spaced out, they get super pissed because they're like, that's not condensed enough. It's like, sue me.
Yeah, exactly. I'm just a student here.
They could take 2 out that whole thing, right? And then just say 2k or whatever.
Exactly. So then you say k equals something, and obviously that thing is going to be an integer. So because the addition of integers is going to be an integer. So you guys probably aren't going to have to worry about the pitfall trap of dividing by an integer in these if we're not doing the divides by proofs, because that was like the main thing.
Because integers involve 0.
That, and also you can't assume that it divides evenly, because whatever your result is has to be an integer. So like when you're doing these divides by proofs, generally you'll end up with a situation where it's like you have to take some extra steps to avoid saying k equals n over m, for example. You don't know what n and m are. You can't say that that's an integer for sure. You don't know.
Oh yeah, just lowercase n, not n like the natural numbers. Okay, yeah.
Yeah. Speaking of which, natural numbers, another complication because nobody knows whether it includes 0 or not.
Yeah. So we kind of went through the algebra here. We decided that this whole sum is equal to some constant k.
Yep.
And since 2k, I mean, I know I didn't define k as being itself an integer, but whatever.
It's all good. Yeah, we get you.
2k is even. And our original statement was that this sum is odd. Therefore, we have a contradiction.
Yeah. So generally, the line of wording that people use in every single proof is, thus we have a contradiction, or the therefore symbol. Therefore, there's a contradiction and our original statement must be false. Thus, x plus y is, in fact, even.
right?
Yeah. I mean, this is kind of a janky proof
Super
just
flex
because
on them.
the question is so simplistic. You don't really even
Yeah,
need
it's
to, like, you don't even need you don't need to prove by contradiction. You could just direct proof this. Like, that's actually basically what we did.
It feels like it.
Now that
Yeah.
I'm looking at it, no, this was basically a direct proof.
Yeah.
But this is still a proof by contradiction, right? Because those aren't mutually
So
exclusive.
actually, technically, no, because we did skip a step. The step would be to say that x plus y equals just randomly in the form after you define your x and y be odd integers. Yeah, right at where you have your cursor, actually, you would then say x plus y equals, and then your even definition. So like 2a if you wanted to, and then or 2a plus 1, because here we're saying it's odd. So then you would be able to say that 2a plus 1 does not equal 2k, therefore contradiction. And that would be the general step for a contradiction, because that's what we're setting up.
I see. Yeah. Okay. Yeah, I agree. This is probably incredibly overkill for this kind of statement, but it's more about making sure the problem is down.
This statement is literally just do a direct proof.
Yeah.
Call it good.
Yeah.
Okie dokes.
All right, cool.
Contradictions are usually more robust and hard to fuck up, though, than direct proof. So that's why a lot of people like them.
Yeah. Okay, consider the following theorem. If x is an odd integer, then x plus 2 is odd. Give a proof by contraposition of this theorem.
That one I know.
I'm gonna let you guys do this on your own. I'm gonna go get it something to drink.
Sure.
All right. So I would say x plus 2 is even, right? And then, so x plus 2 is even implies that x is even, right? Thank you for typing this up, by the way, Adam.
Yeah, sure.
I know we're kind of putting you on the spot with your typing skills.
Fine. It's good. It's good practice.
Yeah.
Okay. Establish our definitions, and let's see, because we'll have to, in case anyone's watching this later, didn't catch this, we will have to handwrite or type this somehow and upload it. It's not going to be multiple choice, so we have to be able to follow through on these processes and all of that, because he's going to be reading it. I don't know how closely he's going to read it, but you won't be able to just autopilot your way through this necessarily.
Yeah.
So, contraposition, let me write that out just for my own reference, if nothing else.
For sure.
Borrow it from up here.
Yeah, it's that guy. Mm-hmm.
Oh, yes, not P, then Q. Or not, wait, I just completely messed that up. Not Q, then not P.
So then to translate that into the statement, not Q would be x plus 2 is even. So if x plus 2 is even, then x is an even integer. Right? That's the...
Yeah. It's assumed that they're both integers, but... Or both expressions, that is.
Yeah. Okay. And again, just...
This is another weird one. What?
What's up?
I said this is another weird one.
Hmm.
Where it's like, you could actually just, you know, direct proof.
Yeah. I'm just trying to think of where to start, because I was thinking
So when we
We
say
start with your definitions.
yeah, x
Yeah, I
plus
have
2.
those down. I'm trying to think. I think I have them all down now because we just have to.
Oh no, I
prove
mean your
this.
definitions, like how in the previous question you started out by saying let x and y be odd integers, and then you said what they are equal to.
That's this, right?
I'm blind.
Oh, it's got it. What? I guess I'll just do this.
Oh, that also did say odd integer. But yeah, I didn't even see that, so.
Well, we're changing it around, so it's actually this now.
Yeah.
Oh no, that's not our premise. This is, so let that be an even integer, right?
For his work on the slides, he just says like x plus 2 equals 2k. So I don't know if like we could just do that on the exam or whatever. Hopefully.
Yeah, it's
Yeah.
so like that then.
Yeah, and then he reduces by just solving for x. And
Yeah.
then yeah.
Oh, okay. Usually there's like
And then once again, you could just factor out 2, and you have another 2k
that's right,
or
yeah.
2m.
Factoring.
Yeah, and then you're good. And then that's even, and the other one's even, and then that proves it.
Oh yeah. Because then again, you can convert all this to some other constant.
Yeah. And that's, since they're both even, we got it. Celebrate. Once again, I don't know. I hopefully we won't have to go like too in detail about like, you know, defining everything and all. I mean,
Yeah.
I'm sure we'll have to say like an even is
totally
this.
punt here and just write that. Okay. Okay. There you got it.
Gotcha. This last one, I went to his office hours, and I think I understand it, but I'm still a little confused on it. So I'm glad we're going over this one.
Yeah. So floor functions.
Yeah. They round down.
Exactly. Of some value k is equivalent to what would I write for the result here? Like n
K minus epsilon, where epsilon is the difference between k and the floor.
Epsilon. You gotta make me go through the Greek alphabet here.
Whatever, you can make it whatever you want.
Let's make it U.
That sounds good. And U is the difference.
Yeah, I know how to define this in words. I'm trying to think about how to define it mathematically. Because it's like if you fall in between two numbers, you choose the lower of the two. So if it was to fall between 2 and 3, the floor function says it goes to 2 between integers.
Right.
I'm just trying to figure out how I can state that. I guess I can just look at the textbook. It's probably defined in there, isn't it? Was that in set operations? Where do we see this? No.
I mean,
Floor, I
granted,
think
it was in functions 2.3.
Yeah.
we do also know one thing, that since our n are always integers, floor of n divided by 2 will either be subtracting 0.5 or it will be subtracting nothing. So we can go through the case of n is even or n is odd.
Okay. Let me just jot that down like a Taylor for the definition.
In fact, whenever we're working with integers and we're doing division, you should always be looking at the cases of odds and evens.
Okay.
Because division is tricky when we're bound to specifically integers.
Adam, if you look at page 159.
Oh, okay.
They have some stuff.
Oh, here it goes. Yeah. Oh, they just wrote it in English. They have properties of the, okay, here's this table 1 on 159 has properties of floor and ceiling functions. If n is an integer and x is a real number. Yeah.
I don't know how helpful that is, though.
Yeah, because it always assumes, at least this one assumes that you have some real input, not an integer input. Because it's kind of trivial in the integer case. Not kind of, it is. Oh yeah, you guys. There's a graph on 158 that has the steps. Okay.
Oh yeah. That's cool.
So we should. Okay.
Do we want to try to like start with even?
Yeah.
So that'd be like 2k. So that'd be the floor of 2k over 2, which is just k. And then times the, oh, sorry. I should probably let you type that first.
That just reduces to k. Yeah. And by the definition of the floor function, any integer will simply, I guess I need to copy that, but whatever. We'll simply just return the integer. It doesn't modify it whatsoever because it's already on the interval. That's also true for the ceiling function, by the way. So we can do the same thing with the ceiling function. Oh, is this an instance where I can apply without loss of generality? So I don't have to type the whole thing again?
I have an apology to make. For number 4, I misled you. Although I think my answer still kind of worked, but basically I just converted it to a direct proof. I'm going to show you the work I just did, which is actually correct, if that comes out at all. Basically, if x and y are odd integers is saying if x how do I say that? If open parenthesis x is odd, and then and y is odd, close parenthesis, comma, then.
Like this? Or was this whole
parentheses around the x is odd and y is odd. Like so extra parentheses. Yeah. So that's one statement. So then when contradiction, you can say not P implies Q and not P implies not Q. That's what the contradiction is. Again, I apologize. I misled you.
That's okay.
I felt it was off, so I decided to double check, and I thought I worked it out, and it's like, yep, that's the right way. That's how it's supposed to be done.
Okay. So is this wrong up here then? This needs to be altered?
Yeah, so you when you do contradiction, you assume not P, and when you assume not P, you're showing in this case there's 2 cases. So the 2 cases are one of x and y are odd, and the other cases both are odd. So with those 2 cases then, one of them you will find that x plus y is odd, and one of them you'll find that x plus y is even. Thus a contradiction, because you can't have both. In fact, my finishing statement was, thus our initial assumption presumes x plus y to be both even and odd, a contradiction. Therefore, if x and y are odd, then x plus y is even. So if you want, I can walk you through the logical steps of the proof, but it's really short. It's just assume x is even or y is even. The or, remember, is inclusive. So that's what allows it to be one or both. It doesn't matter which you choose for the one because commutative or whatever. So for the one case, we have 2n plus 2k plus 1.
So should I just nuke all of this then?
Yeah.
Well, that's what he did on the slides though, like what you have.
Really?
Yeah.
He did it the way that I did it.
No, well, he did x and y are odd, and then he added them, and then he proved that they were even.
Huh.
Yeah.
Okay.
Because
So
I could
he's
share
fine
my
with
screen
my
real
method.
quick.
Please do. I'm curious. Because the way that I just did it is the way that we're actually supposed to do it. And I know that for a fact.
What he did.
I mean, my way is, I think, as far as I know, still logically sound.
Yeah.
But it's not really the formal way of showing a contradiction.
Hmm.
Can you see my screen? I don't even know if I'm sharing.
I can't. Do I need to stop sharing then?
I think you do, yeah.
Okay, then you can do that. There we go. Contradiction. So if x and y are odd, then x and y, move this, is not even.
Which would be p delta, or p or q. Yeah, that was your initial thing. I think you're right. That's the first time.
I think the second one is better to learn. Because the first way is kind of cheaty. If I'm being honest.
The way he did it?
Yeah, the way he did it is kind of cheaty. You're supposed to do it the second way.
Okay.
Because the second way actually gives you a contradiction. And in the first way, we kind of fabricated a contradiction because we were just like, hey, assume these two things, which was the entire statement. We were just looking at the one case in which the statement was false and showing why that one case is false. So we were showing the falsity of the falsehood, which proves that to be true. So it is logically sound, but it's just not. It's not good practice, is what I'm trying to say.
Yeah. I had an old physics professor that sometimes when people messed up their equation, like, you just showed x equals x. It doesn't say anything.
Oh, yeah.
Okay.
But so, yeah, for that one, you should assume the statement I gave you there, which is if x is even or y is even, comma, then x plus y is even. And then you show how there's a contradiction there.
Okay, if x is even or y is even, then what?
If x is even or y is even, then x plus y is even. But you, in showing the two cases possible where there's either one even or both are even, you're showing that there are two possible results where x plus y is odd or x plus y is even. So if you wanted to work through that briefly, we could.
Yeah, that sounds good. Can you share your screen again, Adam?
Yeah, it's just typing stuff.
But it's just using the definitions again.
So let's just all this stuff's in the way. So let's just leave that up, but we'll just start a new branch. So now we're starting from this statement.
I just noticed that you put the tombstone at the end of the proof.
Oh, yeah.
That. It's the most important part of the proof. It's like I just wrote random bullshit, but this shows that I know what I'm doing.
Yeah. Hey, what's the phrase? Not fake it till you make it. I don't know. It's like, if it looks right, most people, oh yeah, oh that must be right, and then you can just pass off all kinds of crap that way.
Random bullshit go.
It's like walk around authoritatively with a clipboard in any building in the world. Yeah. Okay. If x is even, inclusive or y is even, then x plus y is even. So this is the statement that will lead to two results. And since those results contradict each other, that will prove this whole thing to be false. Right.
Yeah, the two cases contradict each other.
Well, I shouldn't say the original statement. A proposition.
Can you see that?
Yeah, I can see that.
All right, great.
So I don't know if other people will be able to see it, so I'll just type.
They can see it in the recording, but yeah.
Yeah, they should be able to see it in the recording. And so basically what that is
so this is actually
splitting up the
or.
Yeah, so we're looking at, I was actually about to say that, we're splitting up the or as we know it from the exclusive or and the and statement. Those are our two cases there.
Yeah.
Which is why I used that specific wording of either but not both.
Are you comfortable with me leaving it like this? I like leaving it like that. As far
as
yeah,
if you write it like that, that's fine, because it gets the message across perfectly.
Mm-hmm.
So long as the reader knows what XOR is, which they should.
Okay.
And so then you just show it for the specific cases using the definitions as you did before. So for the XOR case, you could say, let X be the even one if you want. Proof is left as an exercise for the reader. Love that.
That never gets old. Okay, so then for the first case, only one of these is even.
Mm-hmm. Again, doesn't matter which one you choose.
Yeah.
Which one do you like more?
Start with X. So so I assume X is even then?
Yeah.
Okay.
Well, before you get to X plus Y, you need to formally show that X is even by using the definition and show that Y is even by showing the definition.
Okay.
Frankly, I don't think he'll care if you I don't think he'll care if you show that, like, oh, n is an element of the integers. I don't think he particularly needs that.
Oh, okay. You're saying you don't need to go that formal.
Yeah. Like, I mean, you can if you want to be extra safe, but
I just want to make sure. I'm hearing a chirping, like a smoke detector battery. Is that coming from either your guys or is that on my end?
Sounds like it's on your end.
You know, I think that might be on my end. I think because I have a smoke detector that's been dying for a while and I've kind of just tuned out of it.
I'm going to take a quick break, lower the sound, and just make sure because I'd like to know.
Yeah, that's fair.
Be right back.
It's got to be super faint though. Like, I'm impressed if you can hear it.
Yeah.
But yeah, sorry for the contradiction thing.
Oh, no biggie, no biggie. As long as the slides also proved that, so I think he won't. I mean, there's no way you could be like.
Yeah, I'm just confused why he went with that approach as well. He should have used the better approach. Well, the better approach. I think that the first approach is better because it takes less time, and is less prissy, but you're supposed to do it the second way.
Gotcha.
I got marked off a lot of points on on my final, actually, I think, for don't remember the number of the class, math 295, I want to say, whatever my proof writing class was. I got marked off because he was like, yeah, this isn't how you do contradiction. It's like, but I proved it.
Yeah.
So I mean,
You know,
he'd be
now
well within his right to mark you off if you did it the way that I did it.
and the way he did it as well.
Yeah. Which is what confuses me, but I guess he figures, hey, I'm teaching this to CS majors. They're not going to use this another day in their life, so why does it matter?
I don't know about that. I think that it's just like one way of doing it, maybe. Like I think the other way works too. You know.
Mm-hmm. Yeah. All right. Well, while we wait for him to get back, were there any additional proofs that you wanted to go over after we're done with the review?
Yeah, I was thinking some of the ones you were talking about the rational with the square root 2 and the other thing you were talking about, because I think proofs is definitely going to be a big. Hi, Adam. I think proofs is going to be a big thing on this.
Yeah.
So I don't think
It
it's
sounded like
yet.
it. Are you sure it didn't do any like beeping when you were muted?
You know, what's this one?
I don't know. Maybe you're hearing things.
No, I heard the beep too, so I don't know.
I didn't. But I'm also deaf, so I don't count as a person.
I don't know if that's true.
Okay, you're right. Maybe only like 3/5 of one.
Yeah. Oh well.
All right.
We'll figure
You
it
guys
out.
want to move on with number 6 since we kind of like explained?
Yeah.
For number,
yeah, number 4 should be self-explanatory now.
Yeah.
So I guess I'll share again. Okay, so back to my original question. I wondered if this is an instance where I can use without loss of generality, since I'm going to show the same thing for the ceiling function here, that if it's even, it just reduces down to k. It trivializes the ceiling function.
You're going to have to tell me what without loss of generality means.
Okay. Without loss of generality means that if I show one statement, then I can also show similar statements and apply that same reasoning without going through each specific case if they're all similar enough that I can do that. The cautious part, or you have to be cautious though, that you don't apply that if the statements have different enough conditions that you do have to work them individually.
Wouldn't that be... Oh, I guess we are working with universal quantifier of n. Okay. Sounds like it works.
Plus, I mean, if it didn't work, you could always just plug it in. It's not too much math.
Yeah.
I mean, you could just say.
You could also just say like, hey, if n is even, the floor equals the ceiling, which is just n over 2.
Yeah, I agree. I heard it again. Did you hear it that time?
Yeah, it's really faint though. It's got to be on.
I didn't hear it.
It's got to be on someone else's end because that's way too faint for it to have come from my place because I have this sound turned down pretty low on the speakers.
It's probably my end then.
Ours was chirping a couple days ago because we had a gas leak. Yeah. Or I don't know if that's the same thing, but something was beeping because of that.
No, loss. I'm trying to find the actual definition without loss of generality. What chapter was that in? Was that in?
That was in the 1.8, I think, or 1.7.
I just skimmed through 1.8. I don't remember seeing it, but I'm just.
1.8 has proof methods and strategy.
Yeah, proof by cases. I'm just looking to see if it's a bolded term or something to find, but maybe not.
Pretty sure it's 1.7.
It comes up. I think it comes up a lot when you're doing by case. Oh, here we go. Page 100.
Oh,
we dismiss case 3 of such and such because it's the same as case 2 with the roles reversed of x and y.
So
we can assume without loss of generality that the statement implicit in the statement is that we can complete the third case using the same argument as the second case, but with the obvious changes of just swapping their positions. In general, the phrase is used in a proof, often abbreviated W log. We assert that by proving one case of a theorem, no additional argument is required to prove other specified cases. Yeah. That is, the other cases that follow, by making straightforward changes to the argument or by filling in some straightforward initial step. Often made more efficient when the notion is of without loss of generality is employed. Incorrect use, however, can lead to errors. Sometimes assumptions are made that lead to a loss in generality. Yeah. In fact,
I don't think you could use without loss in generality in this case, only because like our two cases is even and odd, and like that's more of a sub case. Like we're still in the case of even. So
I was thinking in this instance, like doing all this again, but with the ceiling function instead. It leads to the exact same result. So I mean,
I totally agree that it leads to the same result, but I don't think it's a different case. I think it's still in the case of even. You know, I honestly am not 100% sure, but it sounds like they're focusing on cases, and I don't know if we could say that the second, the ceiling in this case is a case because we're just talking about even and odd, you know.
Okay.
But I don't think it would hurt to explain that either. I mean, he didn't do it in his slides, so I'm just going off of what he's going.
Yeah, it's not a crazy amount of typing, so I'll just do it.
Yeah. Okay, so then we multiply them, and we get k squared. Yay! And then if we do n squared over 4, well, that's 2k squared over 4, and that reduces to k squared. So that's good for the first one.
Yep. Well, actually, I'll do it. That. Oh my goodness. Someday I'll learn how to type properly, not just copy and paste to oblivion, but until that day comes.
I feel like you guys are going to enjoy proof by induction. It's basically, it's a really cool way to write proofs. It proves sequences and summations mainly, where you use a base case and then show that some case proves the next case. So if the case proves the next case, then using the base case, that proves it for the entire interval that you're interested in, which sometimes is just all real numbers. So that's really cool. But
yeah, we had to do some really informal proof by induction for data structures, but I don't know if any of us did that right.
I'm gonna be honest, I did not learn a single thing during data structures because I was just not there.
Yeah, well, it was our professor, so. Okay, so I did all this. What's that?
I had fun in that class, though.
Yeah.
I was the person who asked him to sit up, look into the camera, and smile.
trying to get those emojis, huh?
Yeah.
Then someone did like the really weird photo where they tried to do like a Joker smile on it. Okay. We gotta get serious about this stuff. Okay, so we did this for the even integer. So now we just do the same thing for odd, but then it should show up as a. Oh no, I'm mixing it up with the earlier one. We're not looking for a contradiction here. We just have to show both of these cases are true.
Right? We're proving by cases.
Because it's for all.
This is just a direct proof.
Yep.
Is this enough to just leave it at this though and show?
Yeah, I think so. That's what you did in the slides.
Okay. I mean, for doing skeleton and even in a more formal, you're just showing math with these. There's no like huge leaps in logic. You could say that because it's an even integer, dividing by 2 will always result in an integer, so the floors and ceilings aren't necessary. But you don't even need to put that because that's kind of just intuitive.
Yeah.
The most you would maybe want to say is like it follows that because n equals 2k, it must be the case that the floor of n over 2 is equal to the ceiling of n over 2, which is equal to n over 2.
Instead of having the two separate lines like this.
Yeah, you can just equate it all together.
Yeah.
But you don't have to. Like, what you have right there is, I'd say it's enough because you're just, this question is just asking for a basic understanding of floor and ceilings and that you need to use proof by cases.
Yeah. Okay. Okay, so then if it is odd, so then, well, maybe we should just do that. Okay. And this actually becomes it's going to be a well, let's see. I mean, I could split this up as this over 2, right?
Mm-hmm. You could actually even split it up into separate floor functions.
Oh, yeah.
Because that'll make it cleaner.
Oh,
Because then
yeah,
you can
the floor
define the
function of
first
1/2
part.
is 0.
Yeah.
Right.
Because then you can define the first part as well in terms of what you had before. So it follows the same general pattern. And then you can do the same thing with the ceiling, except instead of 0, you get 1. And then you just follow that logic to its conclusion.
So then this is just, okay. Fancy.
Yep.
I didn't actually define k to be an integer here, but
it's okay. I think it's kind of implied at this point.
It is pretty implied. I mean, hey, if you decide that you hate your life and you want to continue in discrete math, enjoy proving that, like, just the most insane things. Like, you have to prove the commutative property, and it's like, how do you even go about that?
Is that it's real analysis, right?
Yeah.
Yeah.
I'm really just killing myself in that class. I have a C right now. It's not going well.
Yeah. Maybe there's a curve.
Oh no, that is with the curve.
Oh, oops.
I have like a 67%, but that's a C, so
Yeah.
I don't care what I get in the class at this point. I mean, I'm kind of doing it to myself. I'm not showing up to any of the lectures, but in my defense, they're at 9 a.m. and I've been waking up at like 3 p.m. So
Yeah. 9 a.m. is a cuss word around here.
yeah, exactly. Yeah, so I'm just looking to S out of that class because it's supposed to be like the hardest discrete math class anyway. So
what's the C plus D? Oh,
because it's, well, I didn't actually. I should do this. It's
are you just saying
that
that
k plus 1 equals some integer c? That's all.
Okay, got it.
Like
I'm
any
confused what the
integer
point
plus
of that
1
is.
is what?
I'm confused as to the point of that.
He's just saying they're integers.
Because k plus 1 is also an integer. That's all I'm establishing.
Yeah.
Maybe it's a little overkill, but
So instead of redefining another variable, you could just put parentheses around the k plus 1 at the end there and say element of integer.
oh.
That works fine. So
cool. Okay, and then that squared over 2.
Oh yeah, now we got to do the square case.
Yep.
Oh no, new page.
Quick, test your basic algebra skills. What's 2k plus 1 squared?
Yeah.
I already did it. It's 4k squared if you want to just like reduce it on the top, just to save time, you know.
So yeah, with the original form, oh yeah, it's over 4. Oh yeah, we got to expand out the binomial, huh?
Yeah. I could just tell you what it is because
Sure.
I broke it down.
It's just
Yeah. So it's you ready?
1 second. I gotta get these
Yeah.
crazy little brackety things here. Okay.
Okay. So it's gonna be 4k squared plus
4k plus 1.
Yeah, plus 1, and that whole thing over 4. And then you could just kind of break that up.
Yeah.
Agreed.
I'm gonna be a little more aggressive with my simplification here because I'm tired of typing all this stuff.
Yeah, I get you.
You can leave 4k squared plus 4k together. Because they're
I'll
both
leave this
divisible by
together.
4.
Oh, because that'll just reduce.
Yeah. So then you can do ceiling of 1/4 and ceiling of 4k squared plus 4k over 4, which is just k squared plus k.
So
Oh wait,
Isn't it floor?
it's 4, not ceiling. Yeah,
Yeah,
I was
it's
like, wait.
floor. I was like, that should be 0.
I was like, wait a second.
I did
This
this.
doesn't line up with my notes.
This is right?
No, this entire thing is supposed to be a floor.
No, it's floor. It's floor. It's
yeah,
all floor.
not ceiling.
What? Oh my goodness.
Yeah.
Oh, okay. Oh, this is all messed up.
No, the first one's right. You did
No, the
floor.
first one's fine.
No, this is.
No, you did it. Yeah, you did it fine.
Yeah,
Just the
did it
last
fine.
part. The end
Just the second case,
squared
yeah.
over 4. Yeah, just that
That's
one.
This.
That's all floor.
Oh, okay.
Yep, everything
Oh
else
man,
is
I was.
fine.
Yeah, because I solved it and then you put +1 and I was like, wait a minute.
Yeah, it's like, hey, wait a minute. Where'd that +1 come from?
Should use LaTeX. This probably faster somehow. Oh well. Oh, I did it.
I mean, hey, at least the next
No,
question is super
stop.
fast.
What's that?
The next question is super fast.
Yeah, I mean, this is really tedious, but
No, you're good. You're just being thorough, my dude.
so this is 0 because that's floor.
Yeah, it's 0,
Correct.
and then that's just that. Yeah, and then when you multiply the 2 above that,
Wait, this is
Right.
mismatched.
And so obviously if you factor out the k, you get k times k plus 1, which is what we had before, so.
yes, exactly. That's a better way of doing it. I just multiplied the first 2 cases, but I like that better.
Oh.
Yeah.
Yeah.
You just take k out and then
Yeah.
k times k plus 1. Yeah, and then you're
So at the
good.
end, you can say, thus believe me.
Okay, scary part done. Hooray.
It true. Tombstone, hell yeah. A well-written proof indeed.
We'll do truth with an F.
Yes. Best believe it.
We'll double down on that. Okay, enough games. Okay, cardinality. This should
Cool.
be a little more straightforward. This
Yep.
Okay,
is
so
number of or if the sets have the same number of elements or the
Yeah.
same, they're equivalent in their elements. If they have the same. No, this is.
I
I'm
have
getting
no
ahead of
idea
myself.
what you're talking about.
just number of
I'm getting my
elements.
head
in the
myself.
set.
That's
It's
like
just a
comparing
number.
Just number of
Yeah.
elements.
You
Yeah.
guys just go fire them off. I'll tell you if you're right or wrong. A.
0.
Yeah,
Yes.
I'm gonna type it out. So, this has
1.
one.
Yeah.
Of which,
C.
Yeah.
2.
Yeah. D.
Is that 3? I think it's 3.
1,
Yeah.
2, 3. Yeah, because this is nested.
Yeah. They just incremented.
Yeah.
Cool.
That really threw me off on the homework because I felt like they didn't explicitly describe the whole nested empty sets. or like a subset that only is composed of other subsets, but
Yeah, basically it doesn't matter what's in the set, it's just how many things are in the set. So
I
if
didn't
there's
catch it. You got really quiet.
Yeah, you were like very
Oh,
very
I was
quiet.
saying basically it doesn't matter what's in the set, just like replace any element in the set with a letter of your choosing, and boom, you have however many elements it is. Just
Okay.
like here, one of the elements is the set of the empty set, comma, the set containing the empty set.
It's like you're getting quieter.
Yeah,
It's like
it really
Ah.
is. So
I don't
for
know.
D, how I look at it is like I usually look at the little curly guys, and so like I know the first one that's absolutely one, and the second one that ends because you see an end bracket, and so the first one,
Yeah.
the third one, I mean, you see the open bracket, but then you see another open bracket, so you ignore it. So then you see the two ending brackets, and that closes off.
Because we're only considering it at this level between these two. We're not going
Right.
into the subsets to see what they say.
Right.
Does he
And
expect us
that's
to do power sets?
I believe so. I don't think to an introductory level power set, like nothing too crazy.
Yeah. I mean, you never know. He might be like, "Hey, power set of this Cartesian product of two sets," and it's like, ah.
No, I doubt it.
Oh wait, I don't know if I can say that's not a set, but
It
it's
is a
coordinate.
set.
Yeah,
So it's a set containing nothing.
yeah. And then that's equivalent to the null space in linear algebra, right?
Yeah.
Yeah.
Yeah. Okay.
All right. 1-to-1.
I'm gonna pretend.
So
that
to
I
show
know
1-to-1, I was just doing this the other day. This is where each element in the domain
Has an
maps
image.
to one
Maps to.
codomain, right?
Yes.
I definitely want to get that. There's that picture in the textbook that graphically shows the different combinations of 1-to-1 and onto.
Yeah, I'm gonna
good
print
way
all
to
that
think
out.
about it is a really good sanity check. Visualize the function, and then see does it pass the horizontal line test. If it doesn't pass the horizontal line test, it's not injective.
Oh,
So,
yeah.
for example, x
I
squared,
forgot about
not
that.
injective. Because obviously when you swap on the y equals x line, it becomes the vertical line test. And that's just seeing if it's a function. So if it's not a function, it's not a fucking inverse.
That's right, because 1-to-1 is invertible, right?
Yeah, 1-to-1, you're looking for horizontal.
Yeah.
To see if it's a function, that's the vertical.
Yeah. So, and then a key point of the 1-to-1 is if the codomain can have elements that are not mapped to. That's okay as long as all elements in the domain, as long as those all have one-to-one relationships. It doesn't matter. Like in the example figure 3, the domain has 4 elements. The codomain has 5 elements. So one of those is not mapped to, but that's still 1-to-1 because everything in the domain is handled. Yeah.
Yeah, the important thing is, well, if something in the domain doesn't map to something, then it's not a function.
Right, but yeah, I meant like they don't. Yeah.
You're saying it doesn't have to be surjective.
Yeah, I forget what subjective is onto. Yeah.
Yeah.
Okay.
Which that just means that
Yeah,
the range is the codomain.
Mm-hmm.
So a formal definition for injectivity is you can say if f of A equals f of B, it must be true that A equals B.
Oh yeah, that's right. I use that in some of the proofs.
Yeah.
Cool.
Though more commonly you'll see them use like x sub 1 and x sub 2 or something like that. But
yeah.
Cool. So the first one, so that would obviously be 1-to-1 because all
when it says determine, we can just say the answer, right? It's not saying show or prove, or is determine meaning no, you need to actually prove it.
I think the term
I
of this
mean-
read says it.
So here, I'll show you a really quick way you can
Does it
show
just
it, just
lie?
like a little bit informally, but it still works.
Mhm.
You can just go like literally, so using that definition that I just put up there, you can say a minus 1 equals b minus 1 implies a equals b, like that.
Okay, yeah.
Because obviously you add 1 to each side, you have a equals b. So you just,
Yeah.
if you just show like the few logical steps on like isolating those two variables, you're fine.
Yeah. That's
also
kind
what
of
the
similar to
professor
what I did
did
on the homework.
in the slides as well.
Yeah.
So this is a parabola, so we know that's not going to be 1-to-1 because you can
1 and
have
-1.
exactly your negative sides will still map to the same y value.
So we could say no for that one.
Yeah, because you have
Nice.
plus or minus a equals plus or minus b, and obviously that won't work.
So that again, a plus or minus.
Well, no.
He's
So
saying plus or
because you have
minus in the front.
because you have a squared plus 1 equals b squared plus 1, obviously get rid of the ones, and then you have a squared equals b squared. Take square root of each side. We consider that you have to do plus or minus, and it's resolved. We know that you can't do that for injectivity.
Yeah.
So then,
How do you do that nice little arrow?
oh, I set my autocorrect. Oops. I set up my autocorrect so that if I do this, it just makes the arrow. If I do that.
That's
So
cool.
Huh.
that
Okay.
is control math autocorrect options. And then you can go in here and you can, where did I do it? Is it here? One of these, you can force it to do certain things. It's actually almost like LaTeX in how it works with some of these like slash commands.
That's pretty great.
Yeah. So like,
Huh.
let me try one. Yeah, like that. You know, a little
Nice.
dot.
Cool.
C dot. Yeah, and the little multiplication dot. So
Sounds good.
I've been trying to find shortcuts and stuff to type all this up faster and make it look nicer without, yeah. Okay, so subtract 1 from each side, we get a squared b squared. Still hate the way they do exponents here, but whatever.
Yeah.
And then from here, square root of both sides, but we cannot say that they're equivalent.
Yeah, you just get plus or minus a equals plus or minus b.
Hey guys, sadly I'm gonna have to go at 3, so we might have to do like a speed run. Sorry,
yeah.
Speed run
sorry.
it quick.
Yeah.
All right.
Because I don't know. I would transfer the host over, but I don't know if that'll keep up the recording or how that'll
This
work.
is getting to 2 hours anyway, so
Yeah.
we can probably try to.
Yeah.
Sorry.
Okay.
Yeah. No, you're good.
Big O.
All right. Well, all right. C, does it pass the horizontal line test?
Yes, because it's hyperbolic.
Yeah. And
Right?
each element is unique.
Yeah.
Yeah. It's like
And
-2.
then
is
floor
fine.
function, no, because
Ceiling
you'll
of
have
n
what?
over 2. Ceiling of n over 2.
The ceiling, not the floor. Yeah.
Oh yeah. But it's still no, right? Because you have
Yeah, that's something called
Yeah,
a step
I agree.
function where it
step
jags
function,
up
yeah.
like that.
Yeah.
so. Yeah. Okay. So big O.
Wait, why is D no again?
Because it's a step function, so it has.
If you graphed it out, you'd have a bunch of horizontal bars.
Gotcha. Okay.
Yeah. So you could have real numbers that.
The function would look like a staircase.
Yeah,
basically.
exactly.
Gotcha. So are there
Because you had
elements
one-
that are the same thing, like
And
0?
a ceiling 1.3 and 1.5 both map to 2.
Got it.
So that's not
Yeah.
1-to-1.
Okie dokes.
Exactly.
Thank you. Cool.
Okay,
Show
so
with
big
this.
O. The key with big O is the witnesses. You have to find some constant C and K to show that our f of x is an element of g of x, right? That's the idea.
Yeah.
Or O of g of x. You're trying to show that that this would somehow fundamentally reduce the behavior of x squared, ignoring some of these little constants and stuff like that.
Yeah.
So I'm used to doing this a little more informally. So I got to try to train myself to do it right and not just say, oh yeah, of course. But
I think the first thing we could do is we could say x cubed.
Well,
plus,
if we only have 15 minutes, maybe we'll just go over the strategy really quick instead of the detailed steps on how to do this.
Sure. Sounds good.
Did he say he was okay with you proving it with limits at all?
He didn't say anything about limits,
what?
I don't think.
Because big O is just end behavior, so you could use limit as x approaches infinity.
Oh yeah.
Then just main limit theorem at end.
Yeah.
But
I don't think like he'll allow that one though. I think he's just looking
Yeah.
for C and K.
yeah, probably not.
I mean, this is how I proved all the ones on the homework 7. I really followed the format the book laid out, which is something like choose a C, show that f of x is greater than that, which is usually trivial, then show that this is less than g of x multiplied
by that C.
Or this is not C, this is K, multiplied by some C.
Right.
And then as a result of that, absolute value.
And so K can just be, because I was having a problem with that the other day. So K can be anything as long as anything after K can be, as long as anything after K, the g of x times C is higher.
I think that's the form. I'm just kind of going off memory with this, but it's something like that.
Yeah. So like, for example,
So in this case, and you may have to do some algebra, especially with these rational ones. You can probably you'll probably have some way of doing some sort of algebra to simplify this down so that your leading term will be x squared. If you're at that point, then you're on the right track. Because
well, you could do what we have is less than or equal to x cubed plus 2x over 2x. And then you could do that is less than or equal to x cubed over 2x, which is less than or equal to x cubed over x, which is less than or equal to x squared, and thus x squared.
Sure.
I could just share my screen and show you what the professor did too.
Let me
all right.
Just this thing. So he basically said, hey, this is always going to be smaller than that. And then he just kept reducing. And then he basically divided these two. Do you see my screen, by the way? Sometimes I don't even know if I'm sharing. Okay.
Yeah, we can see it.
Yeah, and so this breaks up into two parts. And then this is less than or equal only when x is greater than 1. Because you could put 0, and technically the equation before it, this plus 1 would be bigger. So you have to say, hey, it's greater than 1. And then you just, like Adam was saying, if you see x squareds everywhere, you're on the right track, because then boom, you could do that. But
all right, yeah, I like that.
My question is it okay to also say k is 2 and c is still 3 over 2? Okay, yes.
You will get a different C value, but there are infinitely many. If it is of that big O, and usually it starts with the assumption that this is true, and we just have to show why it's true, then there are infinitely many C and K values that will make that true. Gotcha. That's what the book said.
And if we have to show that it's not true, we're probably going to be doing proof by contradiction. So
if K, is this the only unique answer for this C though? Or there's infinite Ks, like you're saying?
No, they come in pairs. Pairwise, they're tied to each other, but there are infinitely many pairs. So if you choose a different C, you'll have a different K.
Okay, Gotcha.
But they're connected pairwise.
Gotcha. Yeah, I'm just trying to think of like where and what scenario would this be different? You know, like how.
It's like, I mean, I think of it like if I was to try to bring it back to a CS analogy, it'd be like, do you start with an array of 10 elements or an array of 1,000 elements? If you have a big O of n squared, it's still going to be n squared whether or not it's 10 elements or 1,000 elements.
Gotcha.
That doesn't change because the big O is reflective of the operations and such that you do on it, not the size of the data set. That's arbitrary. That's why big O is so valuable, because it's a way to abstractly evaluate the efficiency of an algorithm, or not necessarily the efficiency, that's probably the wrong word, but the relative time scale or number of operations compared to a different algorithm. So if you have a sort algorithm that's log n, that will almost always be faster than one that's n squared, unless you're dealing with very small data sets where log n and n squared are very close together. But they'll diverge rapidly once as your data set grows.
Gotcha. Okay. Cool. And then do you guys just
I
want to
have
look
log
at?
n that's even less than n.
What?
Log n is less than n, so I'd hope that it's less than n squared.
Yeah. I just pulled those out of a hat.
Yeah.
So speaking of which, well, the last question then, to zip to the end because Gabriel, you got to go soon, is arranging these in terms of growth. You have square root of, no, it's not square root, that's to the 0.5. You have like 1,000 log n, you have 2n factorial, 2 to the n, and you're just arranging those in terms of smallest to highest growth. And frankly, for that, you could probably just consult, since it's open book, you can just consult one of those growth charts that shows the relative graphs. Just remember that constants added onto the n don't matter. So if you see a 2n plus 1, or if you see 2 to the n plus 1, that's just 2 to the n. You can generally ignore constants, and you can even, I think, for the most part, ignore coefficients. So 1,000 log n can be regarded as just log n for arbitrarily large n's. Again, if you like Aiden said, if you do like the limit definition,
as x approaches infinity.
Exactly. It trivializes the coefficient eventually. So cool. That's not the rigorous definition. That's more like the I'm just a CS student definition as a way to
basically use your calculus 1 for sanity check.
Yeah. That's a good point. Yeah.
Cool. All right. Well, sorry I had to cut it short, but
it's not short. It's 2 hours long. It's not short.
Well, I feel like that was helpful. Thank you guys for thank you for joining. I appreciate it. Yeah, and I'll shoot this over to the Discord when it finally uploads, and hopefully
I'll throw this thing I typed up there on it as well. I'll probably think about cleaning it up a little bit. But I mean, the answers to all the stuff are on the slides, so this is just us working through it ourselves if people wanted to see that.
And you guys should look into those 2 proofs that I mentioned on your own time, in case he throws one of those rationality questions at us, like showing that root 2 is rational, and then showing that a rational number or an irrational number times an irrational number will give you an irrational number.
Sure. I'm just gonna write that down.
Which, of course, that one will not be solved directly because it's hard to do math with irrational numbers.
Yeah. Okay. So show root 2 is rational, and then show that the product of 2 irrational numbers.
No, show root 2 is irrational.
Oh,
because root 2 is irrational.
Yeah. And then show that the product of 2 irrational numbers is also rational.
2 irrational numbers is also irrational. Yes.
Gotcha. All right. Well, thank you guys. I'll see you around, and have a good rest of your weekend.
Yep.
You as well.
All right. Bye.
Bye.